Question 4. A dentist knows from past records that 10% of customers arrive late for their appointment. A new manager believes that there has been a change in the proportion of customers who arrive late for their appointment. A random sample of 50 of the dentist's customers is taken. A. Write down a null hypothesis corresponding to no change in the proportion of customers who arrive late, and an alternative hypothesis corresponding to the manager's belief. So we're in the realm of hypothesis testing for this question. Now, with no change in the proportion of customers who arrive late, that's our given 10%. So our null hypothesis, which we typically note as H0, is that the probability of customers arriving late is 0.1. It's equivalent to 10%. An alternative hypothesis corresponding to the manager's belief. Now, this manager believes that there has been a change. And we're given hints in the question. If we look at part B, we're going to be using a 5% level of significance to do a two-tailed test. Now, two-tailed tests occur when we say it is not equal to the original percentage. This means we don't know if it's less than or greater than, but what we do assume is that there has been a change. So this is our alternative hypothesis. So part B, using the 5% level of significance, find the critical region for a two-tailed test of the null hypothesis in A. You should state the probability of rejection in each tail, which should be less than 0.025. So on a two-tailed test, we're trying to work out that if there is a change in this 10% of customers who arrive late, how many customers would indicate that this percentage should be lower, and how many customers would indicate that this percentage should be higher. So we consider our distribution first of all. Now, these customers are either late or on time, so this is a binomial distribution with two outcomes. We've got 50 patients in our sample and a probability initially of 0.1, so 10% that they arrive late. So first we're going to look at the lower end. How many customers arriving late would mean that this percentage of 10 is too high? So we're trying to find the number of customers where cumulatively the probability of them arriving late would be less than or equal to 0.025. So we'll look for this on our calculator. So we want to find the value in this binomial distribution that gives us an answer or a probability less than 0.025. So let's go into our statistics mode, number 7, and let's go down to our binomial cumulative distribution, which is number 1, and we're entering our variables. Now the x value is the one we're trying to find, so I'm just going to skip that for now. The total number of trials is 50, and the probability is 0.1 for this question. Having done that, I'm now looking for the lowest value that is less than 0.025. So let me start with 0. If I push equals 0, let's do shift and again. 0 is 0.005. Now that is certainly less than. That's good. So let's try 1. 1 is 0.0337. Now that is greater than, which means we've already found our lower bound, and that is 0, because that gives us this answer here of 0.00515. Now we're going to potentially need this value later, so I'm going to store it in my calculator as A. So on our calculator, we found this value to be 0, and we've stored this value as A. This means that if no customers arrive late, then we assume that the percentage should be lower. To consider the upper limit, so the number of customers which, if exceeded, mean that this 10% is too low, we want the probability that any number of customers greater than this critical value be less than or equal to 0.025. Now on our calculators, remember, for binomial distribution we cannot calculate greater than, So we need to rearrange this. When we look for something greater than or equal to x, that is the same as 1 minus the probability of it being less than x minus 1. Rearranging this again and being very careful with our inequality sign, we are looking on our calculator to find a probability for x being less than x minus 1, which is greater than or equal to 0.975. So now I'm looking to find a value of x that's going to give me a probability greater than or equal to 0.975. Now there are a total of 50 trials, and so there's a temptation to try a large upper number, so let's see 49, probability 1. What actually happens with the binomial and cumulative distribution is that our probabilities often build up far quicker than we're expecting. So potentially a good first number to start with might be halfway, 50. Still 1. So let's halve it again. This gives us a logical way of getting through the numbers. So let's try 12. Still very large, but certainly closer to what we want. So let's try 10. 10 is still much larger, so I don't know, I might jump down. Let's go 2. Let's try 8. 8 is 0.94. Now that's too low. So let's try 9. Aha, 9. 0.97546. So this is the first point at which this has gone above 0.975. So let's store this number on our calculator as B. While we're looking at this on our calculator, let's just look at one other way in which we can approach this problem. When we select binomial cumulative distribution, number 1, we could choose option 1, which is to see the probabilities as a list. The downside to this is that we do need to have a ballpark of figures that we are assuming to be in the range we want before we jump in. So we knew that 8 was too low, so let's put in the values of 7, 8, 9, 10 and 11 just for now. Once you've put in the values you want to test in your table, if you hit equals, we had a group of 50 and our probability was 0.1. And now you can see in this table, we can see how the probabilities increase for when x was 7, 8 and 9. And so in this table, we can quite clearly see 9 is where it went over the 0.975. So just another way of finding these values. And again, if you have the ballpark numbers to jump in with, this is great. So we found this value on our calculator to be 9. When x is less than 9, we've got a value of 0.9754, which we've stored as B on our calculator. So we have our x minus 1 value of 9, which means the value of x here is 10. So we're looking for x being greater than 10 in our critical region. So our critical region has the two parts, the probability that x is 0, which was 0.05 and so on, which is stored as A on our calculator, and then the probability that x is greater than or equal to 10, which is 1 minus B on our calculator, which is 0.0245 and so on. Part C is asking us to find the actual significance level of the test based on your critical region from Part B. Well, our level of significance is the sum of those probabilities calculated in Part B. So we have a level of significance equal to our two values. So we have A stored on our calculator and 1 minus B on our calculator, which gives us a value of 0.02969 and so on, which is 0.0297 to 3 significant figures. The manager observes 15 of the 50 customers arrived late for their appointment. With reference to Part B, comment on the manager's belief, while 15 is certainly greater than 10. Since 15 is in our critical region, it supports the manager's belief that there's a change in the proportion of customers arriving late, and in fact the 15 would indicate that this 10% is actually lower than the current value.